Thanks, Chairman. Good afternoon, ladies and gentlemen. My name is Zheng Li. I come from Peking University of China. The title of my presentation is The Influence of the Dynamics on Dynamic Fracture, Brittle Fracture Process. I have divided my presentation into 5 parts. So first we start from the first part, introduction. You know, for the brittle fracture behavior of material is very complicated if especially under complicated conditions. For example, this is just like a complicated stress states. Normally the crack will be the mixed mode crack, not the pure mode 1 fracture. Especially is under dynamic loading, there the process is very complicated. And if we think about some kind of geological material structure, they always have some the multiple cracks inside, and there's some hole or damage around the crack, the moving parts around the crack near the crack tip. So there will be make the fracture behavior more complicated to understand. So firstly, if we will consider about mixed mode fracture, there are some already published work about the dynamic fracture toughness, use the strain gauge and the optical method to measure. And if we talk about crack propagation, normally we have to use the optical experimental method to study this problem. And here we want to use the semicircular bending specimen, because this kind of specimen is has a simple geometry, and they have a long crack moving paths and easily to control the fracture mode, and also easily to be designed and fabricated. And if we talk about crack interaction with damage, there are also some work about that. There's a numerical analysis and independent work, but most of them is based on the static loading the condition. If consider about the dynamic fracture process, the dynamic loading, this is so difficult to analyze. And if we use the experiments to study dynamic fracture problem, normally there's their impact toughness use the Sharpie. But this only you can get the toughness of the material, but you couldn't use the parameter to study the dynamic to study dynamic fracture problem. Use the how to say the parameter. This is just compare the toughness of material. You couldn't use in the dynamic fracture analysis. So there's only use the optical method to study dynamic fracture. One is the photoelectric method. But you know, around the crack tip there are so many tiny patterns. You couldn't get the exact result around the crack tip. This is the cohesion gradient sensing method. But compare these two optical methods, this one is the caustic method. You can see they only have a very simple pattern and around the crack tip, so you can get the crack tip around this area, the mechanical behavior exactly. So here we prefer use the caustic method to study our problem. So let's move to the next part. I will introduce briefly about the dynamic method of caustics. This method is very powerful to study the fracture problem, because this method is very sensitive to the stress concentration area, especially around the crack tip. For example, if we consider a parallel the light rays incident on the specimen, and this specimen under loading and around the crack tip, they have the dramatic length thickness and the refractive index change. So you can see if the light rays transmit to the sample And after that, behind this specimen, we can put a screen, and you can find there the dark spots, and around the right circle. This is the caustic pattern, and this is because the optical path changed around, especially around the concentration area. They have a very strong, very high string gradient. So they're the result. So this we think use the caustic in the mixed mode dynamic fractures theory. So we can use the mapping equation. We can get the caustic curve for the mixed mode, and this is the ratio mu. It means the K2 over K1. And if you think about only mode 1 fracture with the different the crack moving speeds, and we can find the pattern will change a little bit. This is also, we think about the mu, I mean the K2 over K1 is the different value we can consider about the crack moving speed. You can see if the crack moving speed is lower 500 meters per second, this is almost the formula is the same like a static case. So our dynamic fracture is that further is experiments, and we use the PMMA as the brittle material because this is a transparent and very tough engineered material. So we use this design make the specimen. This is a semicircular bending specimen, and this all use multiple spark, the shaving high-speed camera to record the caustic pattern during the crack propagation. And I show you some results. One is about the crack is the compared to the central, there's a symmetric crack there too, and you can see they almost start at the same time, but they have a little bit different about the crack, the tip position, because it's difficult to fabricate exactly the same to the experiments, and their velocity almost the same, and this is the energy release rate almost the same value. If they're a little bit different, I mean the lines is a little bit different. One is moving fast, one is slow, and they compare. This is the stress intensity factor. This is the energy release rate. You can see they have the different. So even the moving velocity is different. Even the initial time is different. So they have the interaction between each other. This is have two cracks on the same side. And this is the same length. And you can see one is close to the center, they move faster. Another one is just stay. And this is the stress intensity factor. You can see at the beginning they are compete with each other. After that, one is move and one is no energy to move. And this is two. One is a different length. And you can see only one move and another one just stay. So you can see the crack, they have the competition with each other. This is if there are some damage around the crack moving paths. So we can see. One is a single hole around the crack tip. So they are at the beginning, the crack move, and then they have stay, rest, about say 200 microseconds. And then they move again. So this is at the beginning, this is mode 1 fracture. After that, still mode 1. And this is around the crack tip. We have 4 holes, tiny holes. So I mean, maybe difficult damage around this area. And so they also have the delay. But the crack at the beginning move. Then they have changed the direction to the because they have a hole to the tube, the whole tube. Then they stay. Then they move, and this you can see the crack propagation deviated to the original mode 1 pass a little bit. And this is, they have a tiny hole around close to the crack moving pass. So there you can see they also have the stay. The crack around this area just rest, and they will wait, and then they move again. And also they have the change the moving path close to the damage, and even the speed, moving speed at beginning and then later they will be changed. This one is also we want to consider there around this crack tip, the surface, use the hammer, give the impact. There's some the damage around this area. So you can see this is the green line, the red line is the perfect, no damage around the crack tip. This is you can see the transparent crack. So you can see the result at the beginning, the crack start moving, the time is different, and even the velocity is different. This we think about there the damage near the crack path, moving propagating path. So you can find that there is also the crack moving and their energy, even the speed, they change. So before I finish my presentation, I would like to conclude my talk. First, I want to say that even the results show that the parallel cracks, when they propagation, they should compete and interact with each other. And mostly one is move faster, one is slow, maybe stay there, couldn't propagate. And if they are around the crack tip area, or even the crack moving past, they have some tiny multiples and the damage. They also infect of the crack moving the path and even the velocity, even make the crack stay there a moment. So this is all the result. I thank the National Basin Research Program of China's support. Thank you very much for your attention.